we were talking about lines, linear equations, slope, things like that. And we mentioned that you can find the slope of a line that connects 2 points through a very simple formula, y2 minus y1 over x2 minus x1. That is a formula you will want to memorize. Bet your bottom dollar on that. So that's a formula you'll want to memorize. And what you do is you just take your first point, label it x1, y1, take your second point, label it x2, y2. Well, what we then have is something called the slope-intercept form of an equation. Slope-intercept form. This allows us to write an equation in pretty much what is going to be the best way. This is the best ending. Whoops. So the reason it's the best thing is because we can immediately glean the slope and the y-intercept of a line simply from this right here. So let's talk about it. Graphing y equals mx plus b using the slope and y-intercept. So basically, you're going to use the rise over run interpretation of slope, and then you're going to use the b from y equals mx plus b to figure out your y-intercept. Let's look at that together. Let's graph the equation y equals negative 2/3 x plus 1. Well, look, we can read right off of this exactly what the slope and y-intercept are. This is the slope, m. This is the y-intercept. And remember, it's really the coordinate 0, 1. That's where it's actually going to cross through the y-axis. And so that's a point on the graph. So we can make ourselves a nice little graph here. We'll put 5 divots on each part of the axes. Something like that. And we'll graph this sucker. So we can see right here, it's negative 2/3 x plus 1. So the b value is 1. So it's going to cross the x-axis at this point, 0, 1. Zero comma 1. Now the slope is negative 2/3. So first of all, is this going to be going upwards or downwards? Downwards for sure. And then it's negative 2/3. So for every 1, 2, 3 units I go to the right, is it going to go up or down 2 units? Down. It's going to go down 2 units. So this is a good little refresher. So it's going to go 1, 2, 3 units to the right and down 2 units. And then we just continue that trend. It didn't like that. Here, I'll just redraw it. It's actually a lot harder to draw than you think. Okay, let's just do 2 lines. Here we go. So over 3 units, down 2 units, something like that. There we go, that works. And there's your line. You can put arrowheads on either end. Like we said, it's going down. Let's see, it goes 3 units over, 2 units down. Three over, 2 down, because the slope is -2 over 3. And that's how you can graph a line using the y equals mx plus b form, using just the slope and what is basically just a point on the line. It happens to be the y-intercept, but it's still a point on the line. So really, if you know the slope and you know a point on the line, any point, you can just start by graphing the point and then use your slope interpretation to find a second point and then extend the line in both directions. It's really pretty good stuff. Make sure everyone's in here. Okay. So a similar idea, plot the point containing the y-intercept. So 0, 2, blah, blah, blah. Nothing all that special. Over here, let's say you wanted to plot the function 2x plus 5y equals 0. Well, that's not in your y equals mx plus b form. You also don't want to do it using intercepts like we did last time. We did one where we figured out the x-intercept and graphed it. We figured out the y-intercept and graphed it. That's not really going to do for us this time. The reason is it turns out this thing has both the same x and y-intercept, and that is the point 0, 0. So you're not going to get 2 separate points. So back to the drawing board. Okay, solve this for y. Get y all by itself. So you got to move the 2x over. Move it over, subtract it over. You'll get 5y equals -2x. Divide both sides by 5. Get out of here. You're going to get y equals -2 over 5x. Now, do you see a plus b over here? Do you see a plus b if you write it in y equals mx plus b? No, so it's implied that the plus b is secretly plus 0. And that is your b. So for this one, the y-intercept is 0, 0. It always has an x value of 0. And then we see the y component is also 0, straight up from the formula. And then the slope is -2 over 5. So it crosses through the point 0, 0. The slope's -2 over 5. Let's go graph that bad boy. Let's see how much of this we can just preserve. You can do it. There we go. Hey, give me a little round of applause for that. Go ahead. And out there in the Zoom sphere, everybody in here, please applaud me. Applaud me now. Thank you very much. Go ahead and double your efforts. Make that applause really real. Just, yeah. Now, why did I do that? Well, it's because it's 9:18 in the morning. Now, you know, it's funny. When I was younger, we would complain about like having to be up at 7 in the morning. 9:18 is not so bad, but here's the thing. Some of us, we work different lives. We stay up different times. We all have different responsibilities. So I understand 9 in the morning can be very tiresome. Me personally, I sleep only 5 hours a night. And I would love to sleep more, but my body just wakes me up. It just wakes me up. So whatever, here we are. We're graphing y equals -2/5x. We already said the slope was -2/5. The y-intercept is 0, 0. So if the y-intercept is 0, 0, that means this guy travels through what is called the origin, the very center point. And now it's going to fall again because it's a negative slope. Every 1, 2, 3, 4, 5 units I go to the right, it's going to go down 2 units. So here is a second point on there. So that when I graph this thing, and I've learned the hard way to just graph one line on top of another like this, whenever we use these controls. You get something like that. It crosses through the origin like it should. And if we draw our cute little triangle, basically what's happening is every 5 units I go to the right, and you can draw the triangle anywhere, it falls 2 units. Because it's a negative slope. So all kinds of interesting things happening with this one. Now, last time we talked about the 4 types of slope. I won't redraw them all. You could have positive slope, and that looked like, well, kind of like that. Where as you go from left to right, it looks like you're going uphill. You can have negative slope, which is kind of like that. As I go from left to right, it's going downhill. You can have zero slope, and that creates a horizontal line, or maybe I can do that. That creates a horizontal line, nice and flat. Or you can have what is called undefined slope. That creates a vertical line, straight up and down. Well, here's the skinny. How do I actually write? We know how to write equations now for lines that have positive slope. It's just an equation, and the slope is a positive number. Why does that keep showing? Tell you what, technology, right? It's not even worth ranting about. We all know it's going to break. We can write equations with negative slope. How do we write an equation with zero slope? How do we write an equation with undefined slope where there's not even a number to plug into the y equals mx plus b form? Not quite. Backwards, yeah. Basically, when I say zero slope, I literally mean the number 0. So let's look at how we deal with horizontal slope, or rather zero slope and horizontal lines as a result. Let's play pretend. Let's say we have a line that crosses through the y-axis. Whoa, that's not a line. You lied to me. Here's a nice horizontal line, nice and flat. It's going to cross through this point here. Let's just say, for the sake of argument, that's the point 0, -2. That's the y-intercept of this line. Well, what is the slope of this line? 0, yeah. What is the slope of this line? Well, it is horizontal, so it has 0 slope. And again, I use the word 0, I mean the mathematical number 0. It's not 0 because the x-coordinate up there is 0. It has nothing to do with this 0 over here, in other words. That's just a coincidence. So I know what the y-intercept is, I know what the slope is, so all right, let's try it out. Y equals 0x, And then since the y-intercept, it's the meat and potatoes of it is -2, I would put -2 there. You don't need it, do you? Because what's 0 times anything? 0. So if I do 0x, I mean, I'm not wrong to write it this way, but it's kind of unnecessary because multiplying by 0 doesn't do me any good. So really, I can break it down to just this. Y equals -2, and that's it. And that's all she wrote. In other words, the equation of a horizontal line is just y equals a, some number a, or we'll call it b, I'm sorry. Where b is just the y-intercept, basically, where it crosses the y-axis. And that's it. That's it, Chip. That's it. What's really cool about that is that says y equals -2. X isn't in there anymore. So any x value I pick, the y value should always be what? In this case. No matter what x value I want to plug in, what should the y value always be? Exactly. So if I come over here, let's say this x value over here is x equals 4. What's the y value going to be? Always -2. So this point is 4, -2. What if I get exotic, come over here, and I use an x value of -3? What's the y value of this point going to be? Still -2. It does not change. So all this equation is expressing is the idea that no matter what I do to x, the y value stays the same as -2. So now when we think about a vertical line is straight up and down. Now, instead of the y value always being the same, what value is going to be the same? Always. Well, in this case, a horizontal line, the y value never changed. For a vertical line, it's going to be the x value that stays the same. So let's gussy all this up. Now for a vertical line, I'll move this over just a little bit. Give myself some breathing room. For a vertical line like this, let's say it crosses the x-axis now at the point 3, 0. That's what this point is. But no matter what, because it's an x value, it's because it's a vertical line, the x value anywhere you go up and down is always going to be the same. It's always going to be 3. You might have the point 3, 4 up here. You might have the point 3, -2 down here maybe. But the x value is all the same. Thus, this is going to be an x equals equation. This is the line x equals 3. You have to be careful. X equals 3, if you're just in one variable, which it appears to be, on a single number line, you just click a single point on that number line, and that's your graph for it. Since we're expressing this in 2 variables, and we still want to express it on an xy coordinate plane, it's got to be a vertical line now. So an equation of the form x equals a, where a is just some number, creates a vertical line that crosses the x-axis at the point a, 0. That's how you create equations of vertical lines. Remember, this is if you still want to graph it in 2 dimensions, 2 variables on the XY coordinate plane. And so that's how we're going to handle vertical and horizontal lines. Long story short. We're talking about function notation. No, not yet. So horizontal and vertical lines are pretty interesting. Finally, our last concept we'll talk about in this section. Slope is the rate of change. Slope is the rate of change. That's a good way to explain this. Let's just look at a graph of a line. Often in math, we want to measure the effect of one variable on another. Usually, in the simplest case, we measure the effect that the independent variable x has on the dependent variable y. Of course, if I spelled things correctly. So you're talking about the independent variable x. It's called independent because it gets to go out and do whatever it wants. X can change as it pleases. Y is waiting back at home and has to adjust around what x does. That's usually the way we set up this relationship. Of course, it's arbitrary. I could say y is the independent variable and x is the dependent variable, but that's just how we like to do it. What we do when we have a graph of something, let's say we have a graph of this horizontal line here. I'll put little arrowheads at the end. What we like to do is we like to change x. In other words, we like to move along the x-axis and see what happens to y as a result of our changing x. But with a horizontal line, as I increase x, what is the value of y doing? It's staying the same. That's exactly right. Let's say that, just for our example, let's say this is the point 0, 17. Let's say this is the point -5, 17. And this over here is the point 4, 17. Look what's happened. X has gone from -5 to 0 to 4. X has experienced changes. But has y changed? No. So in this particular example, X changed a lot, but y didn't change at all. So X has no impact on y. Now, let's think again. Well, X changed, y didn't. Separately, independently from that, just kind of put that pin in that. Let's come over here. What is the slope of this horizontal line? It has a slope of 0. But that makes perfect sense. The slope of 0 tells me that as x changes, for every 1 unit change in x, y changes by 0 units. Whoa. We just dropped a bombshell there, Pilgrim. What that means is that the slope is measuring, the slope is literally measuring the impact that x has on y. For every change in x, the slope measures the change in y. That's exactly what it's doing. In this particular example, the slope was 0, so there was no change in y for every change in x. Let's do something else. Let's try another one. Let's say you have this wonderful line. And now let's make our triangle. Let's say, let's use a different color. First of all, would this be a positively or negatively sloped line? Positive. Now let's say that X, for every 5 units, X increases, Y only increases by 3. For every 5 units, X increases by, Y increases by 3. That's that picture. What would you say is the slope of this line? Not 5 over 3, 3 over 5. Rise over run. So the slope is 3/5. And the slope is telling me exactly how much Y changes for every change in X. So the bottom line, the slope of the line tells me how Y changes for every change in X. It's the rate of change. That's the bottom line. This actually has some very far-reaching implications, namely when you get to calculus and you talk about things like tangent lines. Why we care about the slope of a tangent line is entirely important because it tells me how fast a function or a graph is changing at that point. And that is actually one of the most foundationally important elements in all of calculus, called the derivative, related to that idea. So slope is kind of seen as the rate of change. So the percentage of Americans age 20 to 24 who are married. How many of you, maybe your parents, your grandparents, or you might have stories of people from 50, 60 years ago, they got married awful young. How many of you just know that was kind of the trend back in the day, right? People tended to get married young. Now they still get married young today, but it just doesn't happen as often. There's nothing wrong with it. There's nothing right with it necessarily. It's just how the social trends have changed. So what we see is that in 1970, 65% of women between the ages of 20 to 24, their early 20s basically, 65% of them were married at some point in that age group, when they were at some point in that age. You trend this all the way to 2010, completely different picture. Now, less than a third of that, or about a third of that, is now the case. Now, only 21% of women between ages 20 to 24 are married in the year 2010. And I would suspect in 2020, it's maybe gone down a little bit, or maybe it's flattened out and it's about the same as it was in 2010. There are all kinds of reasons for this. There's no one factor that explains it. In fact, whenever you see a change over time and you see trends, almost never can you point to one single factor. It is so easy to say that, well, in 1970, there was sexism and now there's not. First of all, that's a huge claim. I have no idea if that's true or not. Second of all, even if it's partially true, there may be other factors. It could just be that there were cultural changes and women were entering the workforce at a higher rate now in recent years than in the year 1970. In fact, I guarantee you that's the case. So you can see there's a great downward trend of young women in their early 20s getting married. In men, there was still a downward trend. So it's kind of an interesting idea. Let's think about this. Would this suggest that women would tend to have more male partners, or that men would have more female partners in that age group? That's the real question, because wouldn't you expect these to be about the same, because who's getting married and whatnot? Anywho, what you can do is you can look at women. You can say in 1970, 65% of young women were married. In 2010, 21% of young women were married. You can literally say that's 2 points on a line, and you can calculate the slope between those 2 points. You can literally say this is x1. That's kind of bad. Not really a good place to put it, but you call this x1, y1. You can call this x2, y2. You can calculate the slope of the line in between them, and you'll see that the slope is negative 1.1. Here's the interpretation of that slope. What that means is for every 1 unit increase in x, in other words, for every 1 year, y decreased by 1.1 units. It's negative, that's why I know it's decreased. In other words, the percentage of women in that age group that were married decreased by 1.1%. That's what it means. Every year, on average, now this is an average, that's really the better interpretation. Because I'll bet you dollars to donuts it wasn't a nice perfect line that went down. But that's kind of an average. On average, every 1 year between 1970 and 2010, the marriage rate of young women decreased by a little over 1%. So interesting stuff all around. So slope measures the rate of change. Okay. That finishes off that section. Look at us, we're having a good time. We're all hanging out, having fun in the sun. I don't know about you, but I'm having a blast. What I'm really doing is buying time while I open up the next set of notes. And it's just, this is kind of like a little awkward interim period between those two. There's nothing we can do about that. Okay, back to it. Now it's time to talk about linear inequalities in 2 variables. Wait a minute, Josh, you say. We've already talked about linear inequalities with just 1 variable. You remember, let's just refresh ourselves. This may have been a little bit a while ago. Put on your nostalgia caps. Let's turn on some Everybody Wants to Rule the World by Tears for Fears. And we'll take a little look back in time. Remember, if you had an inequality like x greater than 5, well, this is only 1 variable. But more importantly, we have to be careful because we can actually have things that we are meant to graph on a 2 variable XY plane, even if there's only 1 variable involved. That could be a horizontal or a vertical line, remember? So I need to say this is 1 variable and is meant to be graphed on a single number line. What we're going to see today is we're going to have to graph them on an XY coordinate plane. So we graph this, maybe 0 can be in the middle here with Malcolm. And then we would put 5 over here. And let's see, it's all x greater than 5. So how do I graph this thing? What's one of the 2 things I have to do? Am I going to have to do some shading? Uh-huh. Oh, you are absolutely 100% correct. I put a little air of mystery. Was I going to say correct or incorrect? But you knew. You knew. It's an open dot because it's strictly greater than. If I had made it greater than or equal to, I would have filled in that dot. but that's not the case. So, and then because it's greater than, I shade everything to the right. And I am under contractual obligation to make the same joke that I made last time. If I say the word shading, the joke must be said. And I'm under contract. If I don't make this joke, I am going to walk out of this door and I'm going to be fined into oblivion and possibly sued as well. You want to make sure you use really thick shading as opposed to real what? Real slim shading. Yeah. Listen, I've been telling that joke for so long. And when I say I'm under contract, I mean I'm under contract with several various comedy groups and troupes. And they told me if I don't make that joke, because they invented that joke, they want that joke to get out there and want people to laugh at it. If I don't say that joke when the opportunity arises, they will fine me and they will sue me. They might even be a threat to my physical health. And I'm at the point where this joke is so horribly unfunny, I can see it in your eyes. I used to be able to see it in your whole face, but now we're all wearing masks. I can see it out there that everybody hates this joke. And I feel like I'm trapped. I feel like I'm in a prison of my own mind. I have to make this joke. And it's killing me every time a little piece of my soul dies, like when Voldemort creates another Horcrux, and I hate it. I hate it so much. Please, please release me. Release me from this prison. That got a little bit dark. None of that was true, by the way. That was all just stuff I made up. How many of you believed it for like a half second? Nobody. Gosh darn it! How many of you believe me when I'm telling you math things like addition and subtraction? How many of you believe that what I'm saying about math is true? And you don't believe me when some ridiculous comedy story? Guys, I'm so offended. I'm not offended. So, but I'm glad that you can discern the difference between when I'm being serious and when I'm just BSing y'all, because that's pretty darn important. That's a good little filter to have. Okay, so this was graphing in one variable where we're meant to only graph on a single one variable number line. Now we're going to put on our big boy or big girl pants, and we're going to talk about doing it in two variables. And when I say two variables, I didn't mean to stop that, sorry. When I say two variables, I literally mean we are going to do that and that. Now, we're not going to graph single points because these are linear inequalities. We're going to end up doing things like graphing a line. Here we go. We're going to graph that line maybe. And then when it comes to shading, we don't just shade along a single line. We're literally going to have to shade everything perhaps above the line, or maybe we're going to have to shade everything below the line like that. It just depends on what we have. We're also going to see that the line can be a solid line, or the line itself can be a dashed line like this. We're going to see that both cases could come up. The when to use what is just like the dilemma we faced with whether we use an open circle or a nice closed fill-in circle when we had one variable. It's literally you use a dashed line when you're using a strict less than or a strict greater than. So you're going to use a dashed line, not Morse code. If you're dealing with a strict less than sign, that looks bad. A strict less than sign or a strict greater than sign. And then you're going to deal with a nice solid dash line if you're dealing with a less than or equal to or a greater than or equal to. So that's pretty darn rock simple to make that distinction. And then to shade above or below, we're going to use something called a test point. We're going to use something called a test point, but we'll get into the details of that right now. One last thing, on my labs, all this is super streamlined. All of this is super streamlined, meaning you'll graph your line. Now, sometimes it wants you to graph a special way. It'll say, you better graph this using the X and Y intercepts. And so you'll have to do it that way. But then once you graph your line, you can literally select whether you want it to be a solid or dashed line. And then when it comes time to shade everything below or above the line, there's literally just a little paint bucket tool, and you click in the correct region of the graph, either above or below, and it'll fill in that entire region. It's rock simple. You still have to know what you're doing, but the technology behind it is really straightforward as long as you do execute correctly. But that was just a little preview. And oh boy, we got a nice wall of text here. Let's do the wall of text. If we change the symbol equals in the equation ax plus by equals c, and instead of using equal sign, we use a greater than sign. Maybe we use a less than sign, or perhaps a greater than or equal to sign, or we use a less than or equal to sign. We obtain what is called a linear inequality in two variables. So normally you might have written this as x plus y equals 2. Now it's x plus y less than 2. Oh gosh, what are we going to do about that? Well, we're going to have to not only graph the line x plus y equals 2 and pretend it was just a line. On top of that, we're going to have to decide whether the line should be dashed or solid. And then we bring the less than back into the fold and decide whether we should be shading above the line or below the line. Here's another one, 3x minus 5y greater than or equal to 15. Again, you're going to pretend that you just had the equation. You're going to graph the line from that equation. After you graph, then you've got some decisions to make about whether or not you're going to be dashing the line or making it solid. A solution, well, let's think. A solution to a linear equation. A solution is an ordered pair, an xy ordered pair, where you plug the x value in, you plug a y value in, and if you get a true statement out of it, that must be a solution. It's the same thing for the inequality. We're just changing it out, the equal sign with an inequality sign. But a solution is still going to be a point, an ordered pair that you can plug in the x value, plug in the y value, and if you create a true statement out of it, you're gold. That's a solution. It's in the solution region, we call it. And then graphing that thing, you're really just graphing all the solutions. That's what happens when you shade entirely below the line. You're saying everything below the line, everything in the shaded region, any point you pick, you could take the x value, plug it into the x, take the y value, plug it into the y, and you're going to create a true statement out of that. So for instance, and again, we're kind of doing this as an introductory thing. I'm going to graph for you. Let me think about a good one. Let me think of a good one here. Give me just one moment, but it's kind of interesting. You can see the process I'm about to use here. This is the point 0, 3. So now I'm going to graph the line. Right. So here's the line. If I were to pretend this was an equation, here's the line. Now it's a strict greater than. So this actually needs to be a dashed line. So I'm going to dash it. I use a stupid, clever little trick to dash it. I can't just use this eraser tool because it'll erase the entire line. Okay, so we've got our line. It's dashed. Now the decision on whether or not it should be above, be shaded above or below, it turns out it should be shaded above. So imagine the shading was a little smoother. So now here's the skinny. Here's the skinny, Pat. because the line is dashed, what that tells you, you can think of that as an electric fence. Dashed line is an electric fence, meaning you can walk up to an electric fence, right? You can get real close to it, can't you? But should you touch it? Probably not, unless you're looking for some danger or to feel alive, perhaps. But you can walk up to and get just close to an electric fence, but not exactly touch it. What this means is that anything that's not shaded is not a solution. So look, here's the point 0, 0. Is this point in the shaded region? Absolutely not. So if I try plugging in 0, 0, we're going to check if 0, 0 is a solution. That means I literally have to plug x equals 0 in for x, y equals 0 in for y. I'm really asking, is that true? Well, 3 times 0 is 0, 4 times 0 is 0. Is 0 plus 0 greater than 12? Not on your life. So this is a false statement. That's why this point is not in the solution region. It's not in the shaded region. But if I come over here and I pick the point, say, I know it's hard to see, but let's say that's the point 5, 1. What we can do is we can check now if 5, 1 is a solution. And we're going to see it's in the shaded region, but you're not going to have the graph beforehand. This is reasoning for why the graph makes sense. Now we check 5, 1. I plug a 5 in for x, a 1 in for y. And you see, oh, 3 times 5 is 15 plus 4. Is 15 plus 4 greater than 12? Yeah, 19 greater than 12. That is a true statement. So that's why the point 5, 1 is in the shaded region. It's because it is a solution. That's exactly what it means. Okay, I think that's a good stopping point. Don't go anywhere because I'm going to take attendance, of course.